Ladies and gentlemen, welcome to another lecture in Calculus 1. So today, this is lecture number 9. So today we'll be talking about derivatives again, and in this lecture, where we will learn how to compute derivatives using rules or techniques of differentiations, if you want. And we will avoid the definition. As you have seen last time, the definition wasn't the best way to prove, to find the derivatives of functions. So in this lecture, we will see certain rules that will make our lives easier in computing derivatives. So let's get started. So I will start with something easy at first. Something that we will call the constant rule. We will see what happens when we will try to differentiate a constant function. So today's lecture, we will call it techniques of differentiation. Okay. Well, like I said, let's start with the first rule, and the first rule will be the constant rule. So what does the constant rule say? So it says pretty simple. It says that if you take the derivative, so suppose C is a constant, and if you take the derivative with respect to a variable x of any constant, it will give you 0. So this guy here is a constant. And in here, you take the derivative with respect to the variable x. So there is nothing in terms of x inside, so definitely it will be 0. So that's what you need to know. So anytime you have, or you can also write, so you have a constant prime will always be 0. So that's what you need to know, right? The derivative of a constant is always 0. And let's see an example. So for example, if we differentiate, right, the derivative of 7 is 0. So as you can see, 7 prime is 0. If you take any other constant, for example, I don't know, 1000 prime, this will be 0. So keep this in mind. So you see, there is nothing in terms of x here inside. So this is just a constant 7. So there is nothing with x. So there you go. So the derivative will be 0. All right, so that's what you need to know. So keep this in mind, that the derivative of a constant will always be 0. Okay, that's the simplest rule that you can imagine. But there are some other rules as well involving derivatives of functions, and well, there will be functions of variable x this time involved. And the first one that I have in mind is the following, the power rule. So as you can see there, I have the power function, which is x to the n, and I'm trying to find the derivative with respect to x. So in other words, we can write this as, you see, so the derivative, this guy here, right? So the derivative with respect to x of x to the power n is nothing else than you take the exponent. So the exponent goes outside the derivative, right? It goes like this. And you lower the exponent. So it will be n times x to the power n minus 1, right? Or you can write this in the following way. X to the power n prime, you can also write it in this way, is n times x to the power n minus 1. So that's what you need to know. This is the power rule. All right. Now let's see an example. For example, let's take the derivative with respect to x of x squared, right? So what's the derivative of x squared? The derivative of x squared is, according to the power rule, as you can see in our case, n is 2. So x squared prime is nothing else than 2 times x to the power 2 minus 1. right? Which gives us 2 times x to the power 1, which is 2x, which is exactly what we found here. Right? Okay. Now let's use another one. What if we have, instead of, you see, n is a real number. I want to stress this from the beginning. Look here. Of course, it's n. You would imagine that this is just a positive integer or an integer, but it can also be any real number. For example, it can be a rational number, as we have, as you can see in the second example. So this is, let's say, example 1. This is example 2. And now we would like to compute the derivative of this function of x to the power 3 halves with respect to x, right? Well, according to the same rule in this case, n will be, so in this case, n equals 3 halves. So keep that in mind. So x to the power 3 halves. Well, according to the rule, we're going to take 3 halves outside. So it will be, I'll take this in front of the function, and times x to the power 3 halves minus 1, which will give us exactly this guy here, right? It's exactly the same thing. So 3 halves minus 1 is 1 half. So it's 3 halves times x to the power 1 half, which is nothing else than just 3 halves times the square root of x. And anyway, you can just plug in any rational power that you want. You can put it there and you can find the derivative. So that's how we compute the derivative. Keep in mind the fact that this n here, I want to say that again, is a real number which is not equal to 0. So this rule holds for any real power, not just a positive integer, not just an integer, or not just a rational number, right? As we have seen in these two examples. Now let me tell you another example, which is a little bit tricky. You see, what in fact is not tricky, but so the third example is, what if we want to compute the derivative of this function 1 over x? Well, you can write 1 over x as x to the power -1. So you'll have the derivative, you would want to compute the derivative with respect to x of x to the power -1. And of course, in this case, n will be, guess what? Will be -1. So it will be a negative integer. So no problem. You will take so you will have something like this. Let me write it. In fact, let me write it with red. So you have x to the -1 prime. So you will take the -1 out times x to the -1, which is -1 times x to the -1 is x to the -2, which is -1 times 1 over x squared. Or if you want, is -1 over x squared. And that's the final result. Right? As you can see here, that's exactly the same thing with the negative here, keep in mind. Right, this is pretty much the same thing. All right, so these are the 3 examples that illustrate exactly how you can apply the power rule. Once again, I want you to look at the power rule. Like I said, it doesn't matter if the power is, it can be any real number, any non-zero real number. It doesn't matter if it's a rational, even irrational, integer, positive integer, one, whatever. You can put any, n can be anything real, any real that is non-zero. Okay, so this is the power rule. Keep this in mind. And now we would like to go with the basic rules. And let me just start with the following. Constant multiple. So let's look on the left-hand side. You see the constant multiple rule, which says the following. So let's look at this guy. You see, you have inside here, you have the derivative of c times f of x. So in other words, you have a constant times f of x, everything prime. This is nothing else than just c times f prime of x. So the constant goes out in front of the derivative. So in other words, it does not influence the derivative of the function. So that's what you need to know. As an example, I would like you to look on the right-hand side. You see, I have this function here, which is f of x is, so in this case, f of x is 3x squared, right? And if we take the derivative, you see we have a constant here in front, is the number 3. So we're going to take the 3 out, as you can see, and then we're left with the derivative of x squared. But we know by the power rule that the derivative of x squared with respect to x will be nothing else than just 2x. So it will be 3 times 2x, which will give us 6x. Right? It's pretty straightforward. I think you can get the idea, the main idea of this. All right. So that's the constant multiple rule. So once again, if you have a function and you multiply this by a constant, it will not influence that much when you want to find out the derivative of a function. Okay, that's great. Now let's see the other rule. Another very important rule when you want to operate with derivatives of functions is what we call the sum rule. And this guy here, look at it. Right, look at this guy. So you add two functions, f and g, and you take the derivative of their sum. Well, guess what? Will be nothing else than just the derivative of f plus the derivative of g. Well, if I wanted to write it here the right way, I would have written this as df over dx plus dg over dx, which is the same thing, right? So f plus g, everything prime, is nothing else than just f prime plus g prime. So let me write this one here. So f plus g, everything prime, is nothing else than just f prime plus g prime. So that's what you need to know. The derivative of the sum is the sum of the derivatives. And an example on the right-hand side, let's illustrate this with an example. So suppose we add the functions x squared, right, and x. Well, guess what? This will be nothing else than just the derivative of x squared with respect to x plus the derivative of x with respect to x. Well, the first one, by applying the power rule here, so this guy here will give us 2x, and this guy here will give us 1. So it's nothing else than just 2x plus 1. All right, so that's the sum rule. All right, great. Now let's see the difference rule. Well, the difference will be nothing else than just like the sum. The only difference is that we have a negative there. So we have something like this. This is the difference rule. I want you to look at it. So you see, we have that the derivative with respect to x of f minus g is nothing else than just the derivative with respect to x of f minus the derivative with respect to f of g. So in other words, we could have written this. So this is df over dx, and this guy here is dg over dx. Right. In other words, f minus g, everything prime, is nothing else than just f prime minus g prime. So once again, the derivative of the difference is the difference of the derivatives, right? Just like in the same way with the sum. So it's the only difference is that you have a negative sign there, which is okay. Well, this is what you would expect. And now let's see an example. Well, as an example, you have, let's take these two functions. F to be x to the fourth and g to be x squared. So look here, f of x is x to the fourth and g of x is x squared. Well, by applying the difference rule, so the derivative of their difference is nothing else than just the difference of the derivatives. So we will have that this guy, this will be this, minus the derivative of this, with both of them with respect to x. And now at this point, we can apply the power rule, right? So the first one will be 4x cubed, right? And the second one will be 2x. So that's the difference rule. All right, now you would like to see, let's combine the first two rules if you want, and we will have what we call the linearity rule. There's nothing else than just a combination between the first two. Now, why am I saying this? Well, because you see when you have this constant, about that. So you have this constant here. These two constants, in fact, f, a and b, and you have this combination, this linear combination. That's why we call this linearity rule, where with these two functions. So if you take the derivative with respect to x of a plus f of x plus b times g of x, so a and b are constants. So let me write this, so that things are clear. Then we will have that the derivative of this linear combination of f and g will be nothing else than just the linear combination of their derivatives. In other words, the derivative with respect to x of a times f of x plus b times g of x will be nothing else than just a times f prime of x plus b times g prime of x. Again, this is just the derivative of f with respect to x. As an example here, so here we can take these two functions. So let's take f to be x squared, right? And g to be x. And these constants will be, let's say, a will be 3 and b will be, let's say, -2 if you want. So as you would expect, well, we can take the constants out. So it will be, according to the rule, 3 times the derivative of x squared with respect to x, which is this guy here, minus 2 times the derivative of x with respect to x. Well, this guy here is 1. This guy here is 2x. And at the end of the day, we will have 3 times 2x. So this is 3 times 2x minus 2 times 1, which will give us 6x minus 2. Right? So these are I would say, the easy rules. Well, that's why we call them the basic rules. There will be some other rules as well. But I would like you to just have another look at these rules before we go further. Like I said, these are the most basic rules. And we would like to see, let's say, more examples. And let's just start with the following example. I want you to look at this example. I'd like to see some more examples of these basic rules before we go with other rules as well. So let's see. So we would like to compute this first example. In this first example, we would like to compute the derivative of this function, or if you want, we have two functions here, or maybe we can have this guy here should be f of x. This will be a constant, let's say a. This will be, let's say, another constant b, plus times 1, and let's just say this is a g of x. So by the linearity rule, if you want, we can take the 4 out, and this will be nothing else than just, or if you want, you can take b to be 1 and g of x to be, okay, let me put it this way. So it's 1 times 2, so this is b times g of x. So now, and that doesn't really matter. Oops. So b is 1 and g of x is 2. So again, by the linearity rule here, so by the linearity rule, we have that this is equal to 4 times the derivative of f, which is this guy here, as you can see it, with respect to x, plus the 1 that you see here, the constant, times the derivative with respect to x of the constant of g, which is 2. Well, this guy will be 0 because it's the derivative of by the constant rule, and here by the power rule, this will be nothing else than just 4 times negative 2 to the power x negative 2 negative 1, which is negative 3. And at the end of the day, we'll get this result here, right? So in other words, it's just linearity rule, and if you want here, the power rule. But I hope you will, at the end, you'll end up playing with them. It will be so easy for you that you don't need to remember all these rules. It will be just by you just write them up and that's it. So you don't need to stay and look which rule, what it will be just automatic, I hope, at some point for you to apply these derivative rules. Let's see another one. So we have another one. You see this time here, we have two functions. This guy here, look, this is f of x, and this guy here is g of x. And now we would like to apply the sum rule. And guess what? Well, we can write both of them as powers, right? The square root of x can be written as x to the power 1/2 plus, well, we don't need to apply the sum rule yet, right? But now here, we can apply the sum rule. So this will be nothing else than just, well, here, this will be nothing else than just the derivative of x to the 1/2 with respect to x plus the derivative of x to the negative 1 with respect to x. And this guy here will give me this. And this guy here will give me this. Right? So I jumped one step on purpose so that you can see it. Right? So once again, you apply the sum rule, and then you apply just the power rule for each function. Okay, now let's see another example. What if we have something like this? Just look at this. Look at this function here inside. You see when you have this function, this is our function f of x. Now I'd like to find the derivative. Like I said, when you have radicals, you don't want to waste your time with, oh my God, let's compute the derivative of the radical. Maybe it's better for you to write that radical as a power function, because you know how to compute the derivative of a power function. So you don't need to remember all those radicals by heart. So you can do so. Imagine here you have this x to that radical over there can be expressed as x to the power 2/5. So once you do this, let's look at the derivative of this guy. X to the power 2/5 will be 2/5 times x to the power 2/5 minus 1, right? Which is 2/5 times x to the power negative 3/5. All right, great. So I have this guy here, but also I have a 3. So let's not forget about the 3. So once you multiply by the 3, you'll get 6/5, which is exactly what we have. Okay. right? So these are how we apply the basic rules. But now there is more. There are more rules that I would like to talk about. Okay, and I'd like to start with the following. The product rule. This is a very important, and it's not as you would expect, right? The product rule is something like this. Just look at it. So the derivative of f times g is not as you would expect the derivative of f times the derivative of g. Nope. So it's the derivative, it's f times the derivative of g plus f plus the derivative of f times g. So in other words, let me write it in this way. F times g everything prime is f prime g plus g prime f. So that's what you need to know. This is the product rule. So once again, there's a danger, and I'd like you to, f times g prime is not f prime times g prime. Please do not make this mistake. This is very important. That's a danger. Don't do it. So if you write this, then you're in a danger zone. F times g prime, everything prime is not f prime times g prime. Is not for all functions. So I would like you to look again at this rule. It's very important. So once again, this is what we call the product rule, right? Once again, the derivative with respect to x of f times g is nothing else than just f times the derivative of g with respect to x plus g times the derivative of f with respect to x, as you can see here. Or in other words, you can say f times g everything prime is f prime g plus g prime f. So this is the very important. So once again, do not make this mistake of saying that f times g everything prime is f prime times g prime. This doesn't happen. Well, always. It can happen for some functions. There exist some functions for which this happens, but it's not true for all functions f and g. Like it happens, for example, when we have the sum or the difference. So the product, as you can see, it's a little bit different. For the proof, well, guess what? You can use a definition, and you can add and subtract. Just you take f plus x, f of x plus delta x, you multiply by g, and you add and subtract this guy, and you can prove it in this way. But anyway, I will not insist on the proof of this. I think it's more important for you to remember this rule. All right, let's see an example. As you can see here, I'd like to find the derivative with respect to x of the product of these two functions. So once again, I would like you to look at the product of the product rule. So it's written there. So right, f times g everything prime is nothing else than just f times g prime plus f prime times g. So in this case, what do we have? Well, if you look closely, this is nothing else than just, well, the product rule for those two functions that we have, right? So in our case, f will be this guy. So that's my function f of x. And this guy will be my function g of x. So, and we would like to apply the product rule, so let's do it. So this would be f This, as you can see it here, this is f of x. This guy here will be nothing else than just times g prime of x, right? The derivative with respect to x of x to the fourth plus 2. Then we have this is the nothing else than just f prime of x. And this guy is nothing else than just g of x. Well, just by applying the product rule, right? That's what we did here. We applied the product rule. All right. Now we can compute the derivative. The derivative g prime is nothing else than just 4x cubed plus 2 prime, which is 0. So it will give us 3x minus 1 times 4x cubed. And the second one, 3x minus 1 prime will be 3. So it will be 3 times x to the fourth plus 2. And if you do some algebra, it will give you this. So that's the final result. Anyway, here's after some algebra. Okay. I'm sure you can do the algebra. There is no point of explaining things. You just multiply, you FOIL the parentheses, and you can easily see what's going on. All right, that's the first example. Let's see more examples. I want you to look at this guy here. Again, the same thing. So what do you think? So you will have that here. In this case, again, you'll have the product of two functions. But in this case, f will be 2x plus 3, and g will be 5x squared minus 7x. Right? Okay. So let's write this. Okay. And now let's see, what do we get? Oops, sorry about that. So let's see. You see, I have it here. So f prime, let's write it here. F prime will be 2, and g prime of x, let's do it quickly. It will be 10x minus 7. Okay. As you can see, I have, this is f, this is g prime, this is f prime, this is g of x. So here I just apply the product rule. As you can see here. You see g prime of x is here. That's the g prime of x. That's f of x. It's 2x plus 3. Then f prime is this guy here times g of x, which is this guy here. And again, you FOIL, you do the algebra, and you get the final result to be this guy here. Anyway, to be honest with you, in an exam, I wouldn't care too much about the algebra. I just want you to apply the principles correctly. So that's the only thing I do care about. So that's all right. Now let's move to another rule. And this time, if we talked about the sum and the difference, and now since we talk about the product, why not talk about the quotient? So here we go. We have the quotient rule. So what happens when we would like to see, when we would like to compute the derivative of the quotient of two functions? So in other words, what happens if we have f over g everything prime? Well, guess what? It's f prime times g minus g prime times f everything over g squared. So that's the rule. Anyway, I'm not going to go into the proof of this, but that's the rule, and you will see it here as well. All right. So once again, the derivative with respect to x of f of x over g of x is nothing else than just a g of x times f of times the derivative of f with respect to x minus f times the derivative of g with respect to x, everything over the square of the function g, as you can see it here. In other words, f over g everything prime is f prime times g minus g prime times f, everything over g squared. All right. And now let's see some examples. And I'd like to show you not maybe three, actually more examples, why not? I'd like to see maybe 3 or 4 examples. And let me start with the first one. Let's look at this guy here. So in this case, I think it's quite clear. So we have this quotient rule here. So this is the quotient rule. So in this case, our function f is this guy here, it's 3x minus 1. And this guy here is g of x is x to the 4th plus 2. All right, this is pretty straightforward. Let's apply the quotient rule. Well, that's exactly what we do here, right? So we apply the quotient rule, and we have that that this is x to the 4th, right, which is g, so it's the derivative. So this guy here is, this is f prime of x. This is g prime of x. As you can see here, this is g squared of x. This guy here is g of x, right? And this guy here is f of x. So that's nothing else than just, it's pretty straightforward. And now we can compute the derivative of each one of them. So the derivative f prime of x is 3. So it's 3x minus 1 prime, which is 3. And g prime of x is x to the 4th plus 2, everything prime, which is 4x cubed. So that's what we need to remember. And now we can plug them here. Look at this guy here is g prime. Look at this guy here is f prime. And at the end of the day, will be just algebra again, and it will give us this rational function here. So that's the basically how you can compute the derivative of a rational function. Well, as you can see, you have the quotient of two functions. So in other words, you apply the quotient rule. So that's what you do. All right, now let me draw your attention with another example. What about this guy here? As you can see at the top, you have a linear function. On the bottom, you have a quadratic function. So again, you can identify, it's again the same thing, the same story. 2x, f of x is 2x plus 3. Then g of x will be 5x squared minus 7x. And guess what? The quotient rule will apply again. So let's do that. And once we do this, yeah, right? So let's see, who is f prime of x? Let's keep in mind it will be 2x plus 3, everything prime, which is 2. And g prime of x here, if we want to compute this, this will be 5x squared minus 7x, everything prime, which will be 10x minus 7. Right? Okay. So as you can see, we have it here. We just apply here the quotient rule. So here's the derivative of this that we already computed, which is here. And here is the derivative of this, which we computed, which is here. And here is the g squared. So once again, we plug it in. You see, this is 10x minus 7, right? This is the g prime. And this is f prime, which is 2. And we have g and f. And here we have g squared. So this guy is nothing else than just g squared. So this goes by elementary algebra. So we'll leave this to you as an exercise. You just square 5x squared minus 7x, everything squared, and it will give you this. And at the end of the day, you'll end up with this rational function. So that's what so you would expect to end up with the rational function. Okay. Right, so this is the example. But now let's do another one, which is a little bit more tricky, I would say. Look at this guy here. You see, apparently you have the product of the square root of x times this rational function. So let's look at the function first. And let's look at it very carefully. So that square root, as we have previously seen, can be expressed as x to rational power, right? So this guy here is x to the power 1/2. And we can multiply this by x so that we don't need to apply the product rule, then we need to apply the quotient rule. We just multiply them. You have the quotient of two functions, and we can apply just the quotient rule directly. You don't need to apply the product rule, then the quotient rule, and so on. It would be complicated to have two procedures applied at once. So that's what we need to observe. So x to the 1/2 times x, this is what is x to the 3/2. So that's what we have at the top, as you can see it here. Perfect. At this point, we can apply to this guy the quotient rule. Well, beautiful. So this is what you see here, right? This is the quotient rule. All right, beautiful. Let's do it. Once we do this, we have this. First, let me write what you see. We have so my function f here is x to the 3/2, and my function g here will be x squared plus 3. So here f prime of x is, so let's write f prime and g prime. So g prime will be 2x, and this will be 3/2 times x to the power 3/2 minus 1, which is 1/2. All right. As you can see, this is g prime of x here. Right. And this guy here, right, is nothing else than just f prime. And on the bottom, this is nothing else than just g squared of x. And well, this is nothing else than just algebra, and you will end up with this mess here. Anyway, this is just algebra. So this is another example. The main trick here was to observe the fact that you can express radical x as the x to the power 1/2, and then you multiply with x, and then you'll have the quotient of two functions, and then you can apply directly the quotient rule. Okay, let's see another example now. Look at this guy here. Wow, looks ugly. I don't like that. Very ugly. Ooh, whoa, whoa, whoa. Let's see, let's see. You see, now I have here a combination of functions. So this is f. This guy is g. Whew. So I need to compute the derivative of each one of them. What a mess. So again, you can see here I have the quotient rule. So we're going to need that. So, well, let's see. What do we have? So the derivative by applying the quotient rule will have this. And now we need to take the derivative. So this guy here is the derivative of f. And this guy here is nothing else than just the derivative of g. And again, this is g. And this guy is f. And this guy here is nothing else than just g squared. So in other words, is nothing else than just the quotient rule applied. Well, beautiful. Now let's compute the derivative of each one of them. Oh my, what a mess. Well, the derivative of the first one, and let me write it somewhere. Let me write it here, f prime of x. So let's see, f prime and g prime of x. Maybe I have enough space here to compute them. So it will be 5. Ooch, sorry about that. Ooch. So it will be 5 times x to the 1/2. So this is 1/2 times x to the 1/2 minus 1, which is negative 1/2, plus 3 times negative 1 over x squared. And g prime will be is negative 3/4 times x to the power negative 3/4 negative 1, whatever this is, plus 2x. Anyway, we can do some computations here. So the first one will be 5/2 times x to the negative 1/2 minus 3 over x squared. So that's, and the second one will be negative 3/4 times negative whatever, negative 7 over 4, x to the negative 7 over 4. Okay. Plus 2x, I'm sorry, plus 2x. So, okay. As you can see them right here, right? This is the first one. So this is f prime. And as we have seen, this is the second one, g prime. That you see them here, right? Let me look at them with another color. Look at this guy here. And look at this guy here. Okay. Let me write them here again. So f prime is f is 5/2 times x to the negative 1/2 minus 3 over x squared. And g prime of x is negative 3/4 times x to the negative 7/4 plus 2x. So these are the two functions. So enough room, but I think you can see them. But you see them here, right? And this is g prime and f prime. And of course, here we have g squared of x, as you see it here. And now it's just algebra, and I don't want to do it. It's a mess. You can leave it like this. It's fine. So that's the derivative. Pretty messy, but this is how you use at first the quotient rule, and then you will apply the power rule for on both the top and the bottom, right? Okay, I would like you to look at this example again. Like I said, it's a little bit more involved, but it's not as crazy as you might think. But anyway, you should expect examples of this type at the first gateway exam. When you the first gateway exam, let me remind you, it will consist of finding 10 derivatives, and you should expect functions like this. All right. So this was another example, and now I would like to talk about, let me talk about higher derivatives. So as you have seen, we can denote f prime of x, or dy over dx if you want, or if you want to change the notation, we can denote this by df over dx. So this is the first derivative. The second derivative will be f second prime, or if you want, d squared f over dx squared, right? And the third, the same goes for the third derivative, or d or dx cubed, or the n derivative. So what this notation means, you can use these notations, right? F prime, f second prime, f third prime, or the n derivative of f. Or you can use the derivative of f n times the n derivative of f with respect to x and applied n times. That's how we're going to read it, right? So these are the notations for higher derivatives. And now let's look at this function. What we would like to do is to find the first, second, the third derivative, and the fourth derivative. Why not? For this function of degree 5, this polynomial of degree 5. Well, as you can see, this function is a combination of two functions, right? Is a difference of two functions, of this one here, 3x to the fifth and 2x. If you want, you have to compute the derivative of each one of them. So let me just, so this is the function, right? F of x. So the derivative of this, so let me write here, the derivative of 3x to the fifth prime. So I can apply the constant rule and the power rule. So it will be 3 times x to the fifth everything prime, which will give me 3 times 5x to the fourth. And this will be 15x to the fourth. So that's the derivative of this function. And the derivative of, let me write it somewhere here, 2x prime, again, we'll have apply the constant rules, 2 times x prime, which is 2. 2 times 1, which is 2. So this is nothing else. The first derivative is just the difference of the two. It's 15x to the fourth that you see here minus 2 that you see here. So that's the first derivative. Now, we know what the first derivative is. What is the second derivative? Well, the second derivative of a function is nothing else than just the derivative of the first derivative. So this would be, so the second derivative, let's write it here, will be the derivative of the first derivative. And of course, this will be nothing else than just if we 15x to the fourth minus 2 prime, which is 60x cubed, which you find it here. And we keep going. The third derivative will be the derivative of the second derivative, right? F third prime of x is f second prime of x, everything prime, which will be 60 times 3x squared, which is 180 x squared. And we keep going. The same story goes for the fourth derivative, which will be a linear function. So you just keep differentiating over and over again, right? So keep this in mind. When you're looking for higher order derivatives, make sure that you know what the first derivative is. Then based on the result obtained on the first derivative, you will find the second derivative and then the third derivative and so on. Okay, now let me draw your attention with one more example, and I think after this I will stop. So let's look at this guy. Let's find the first, second, and the third derivative of this function. If you don't like the notation, that's fine. You can write this as f of x is x to the negative 1 plus 3x squared plus 4. Well, the only thing that we need to do first, you see we have a combination, the sum of three functions, so we need to find the derivative of each one of them. So let's let me write it here, x to the negative 1 prime, as we have seen, is nothing else than just a negative 1 over x squared. Then 3x squared prime is nothing else than just 6x, and 4 prime is 0. With this in mind, the first derivative is nothing else than just negative x to the negative square, which is negative 1 over x squared plus 6x. And here was plus 0, which is negative, right? Great. The second derivative, we need to differentiate this again. Well, the derivative of negative x squared, again, you will use the power rule. It will give you 2 times x times, it will have negative negative, which will become positive. So this is the, let's say, f prime of x if you want. This is f second prime of x if you want, right? Let's just say this is f of x. Like I said, if you don't like the notation, 6x prime will be 6. And now, once again, if you like to find the third derivative, this guy will just vanish. So 6 prime will be 0. And you'll have only, you're left with only these guys, the derivative of that guy, which will give you negative 6x to the negative 4th. Or if you want, you can write this as negative 6 over x to the 4th. And that's it. So this is how we find the derivative of this. Of this function, right? As you can see, is the sum of 3 functions. Okay, right? All right, I think I'm going to stop here for today's lecture. Next time, so on Wednesday, I will talk about the derivatives of trigonometric functions. You will see that something happens. In fact, I will prove that, because we will make use of the limits that we have learned involving sine and cosine. So we will show that the derivative of the sine will be cosine, and the derivative of cosine will be negative sine. And also we will see how we will apply the product rule and quotient rule or the sum rule involving trigonometric functions. Okay, I think I'm going to stop here. Thank you very much.